The sun is the most powerful force in our solar system, so immense that over 1 million Earths could fit inside it. It provides the heat and light that sustain all life on our planet. Without it, life as we know it would not exist. Yet the sun is also a violent and unpredictable entity, growing more hazardous as it ages. It will become hotter and thousands of times brighter, eventually evaporating our oceans, melting the planet's surface, and rendering Earth uninhabitable. Sunrise is a daily marvel, bringing the warmth and illumination we need to survive. We often take the sun for granted, assuming it will always be there, with sunburn being our primary concern. However, the reality is far more complex. The sun possesses the power to cripple our most advanced technology, unleash energy comparable to nuclear explosions, and pose serious risks to our safety. As the sun continues to age, its life-giving energy will transform into a threat, potentially forcing humanity to abandon Earth and challenging our survival as a species. Astronomers understand that the sun has a finite lifespan. Stars, like all living things, do not last forever. Our existence on Earth is deeply connected to the sun's own life cycle. But how can we understand the sun's birth and distant death when dealing with timescales of billions of years? Just as no one witnesses a redwood tree's entire growth over millennia, yet we know it begins as a seedling, grows enormous, and eventually dies. We can observe millions of stars in the night sky, each at a different stage of evolution. Our sun is a star like those we see at night, so studying other stars reveals the story of our own sun's life. Near Orion's belt, there is a stellar nursery where stars younger than 1 million years are forming today, just as our sun did billions of years ago. Imagine the sun's life as a sundial, beginning at dawn, 6 in the morning with its birth, and ending at dusk, 6 in the evening with its death. Right now, it is exactly 6 in the morning. The sun is being born within what scientists call a molecular cloud, composed of dust and gas debris from countless exploding stars. This cloud is primarily hydrogen, the universe's most abundant element. Gravity pulls these atoms together over 1 million years, causing the cloud to collapse inward. Material increasingly clumps at the center. Picture fire dancers spinning flames. The farther the fire is from their hands, the slower it spins. Bringing the fire closer to the center makes it rotate faster. Similarly, in the molecular cloud, molecules spin more rapidly in the middle, which grows denser and denser until the atoms at the core are packed so tightly they heat up. Compressing air in a model demonstrates this heating, similar to how hydrogen compressed as the sun formed. This process ignited the sun, starting the fires that have warmed Earth for billions of years. The cloud's temperature skyrockets to millions of degrees, so intense that hydrogen atoms collide and fuse, releasing tremendous explosions of energy. This outward force battles the inward pull of gravity. The sun's entire life will be a constant tug-of-war between these two powers. For now, a stalemate is reached. The pressures balance, and the sun is born. It contains over 99% of the original molecular cloud. The remaining material forms Earth and the other planets in a disk around the sun. Scientists widely accept this model of the sun's birth, but theory alone is not enough. The sun is 93 million miles away, making physical evidence scarce. That changed in August 2001 when NASA launched its ambitious Genesis mission. The goal was to bring a piece of the sun back to Earth. The sun's chemical composition is like a fingerprint of the original solar nebula. Capturing a piece of it for analysis is a thrilling prospect. But how do you capture a piece of the sun? Even its outer corona reaches 3 million degrees Fahrenheit, a temperature no probe could withstand. The solution was to collect the solar wind, a stream of particles blowing from the sun at speeds up to 500 miles per second. Earth's magnetosphere shields us from this wind, so the Genesis spacecraft traveled 1 million miles into space. There, it deployed ultra-pure wafers of gold, sapphire, silicon, and aluminum to bask in the solar wind. Particles from the wind embedded themselves deep within these materials. Back on Earth, a daring mid-air capture was planned, relying on a Hollywood stunt pilot. His mission was to intercept the returning capsule as it parachuted down, snatching it with a helicopter before it touched the ground. After years of training with perfect success in rehearsals, the moment of truth arrived in September 2004. The capsule re-entered the atmosphere, but something went wrong. Its parachute failed to open. The capsule tumbled uncontrollably and crashed into the Utah desert at high speed, shattering the precious wafers. For the team, it was a potential disaster. The silence was profound. Disappointment set in. NASA now faced the immense task of salvaging data from the wreckage. The challenge was to extract the solar samples from the broken wafers without further contamination. The samples consisted of atoms and ions, incredibly tiny, with a total weight no more than a few grains of salt. Yet billions upon billions of these particles were collected. While the sun is mostly hydrogen, scientists also expected to find silicon, oxygen, carbon, nitrogen, magnesium, and iron. All elements are blends of atoms called isotopes. The sun holds the original blend from the primordial molecular cloud, offering a chance to look back to the very beginning of our solar system. The team successfully extracted the first atoms, though full analysis will take time. What we know is that Earth is uniquely positioned in the solar system's temperate zone, not too hot like Mercury or Venus, and not too cold like Mars. It is just right for life to flourish. On our sundial, it is now 10 in the morning, 4 billion years after the sun's birth. Animals have appeared. Just 35 minutes later by this cosmic clock, humans walk the Earth. Our bodies are made of carbon forged inside stars. Today, we depend utterly on the sun. Its energy fuels the plants and trees that form the base of our food chain. By evaporating ocean water to form clouds, it provides rain for crops and fresh water to drink. This energy is generated over 93 million miles away in the sun's nuclear core, where temperatures exceed 27 million degrees Fahrenheit. Here, 4 hydrogen nuclei fuse to create one helium nucleus. The resulting helium is slightly lighter than the original hydrogen. This missing mass is converted into pure energy, as described by Einstein's famous equation. This energy is released as photons, particles of light. Every sunbeam is filled with them. Each second, nearly 600 million tons of hydrogen fuse into helium, releasing more energy in that single second than 6 billion nuclear power plants produce in a year. But how does this energy reach us? The journey a photon takes to deliver energy to Earth is extraordinary. The photons that give you a tan today began their journey over 1 million years ago. Some started when dinosaurs roamed the Earth. They fight their way through the solar system's greatest obstacle course, beginning in the sun's dense core. Here, photons zip around at light speed, colliding with electrons and transferring energy, much like balls in a Newton's cradle. The next challenge is the radiative zone, where photons are bounced around by hot hydrogen plasma, zigzagging randomly for hundreds of thousands of years. like pinballs in a machine. Many photons have been trapped since the sun formed and have yet to escape. The fortunate ones finally reach the convection layer. There, they are absorbed by rivers of hot gas and carried to the sun's surface, the photosphere, in about 3 months. At the surface, atoms cool and release their energy as photons once more. These photons stream into space and, traveling at light speed, reach Earth in just 8 minutes. Photons have provided heat and light since the sun first shone. By 10 in the morning on our sundial, they helped create the conditions for animal life on Earth. But exactly how old is the sun today? Scientists discovered a remarkable clue. The sun sings. Massive pressure changes deep within cause vibrations that resonate to the surface, similar to seismic waves on Earth. To hear the sun's voice, scientists speed up these pressure waves 42,000 times, compressing 40 days of vibrations into seconds. Research to calculate the sun's age from its song was conducted at the Big Bear Observatory. The sun's internal temperature and pressure change over time, altering its song, much like pressing on a drumhead changes its pitch. As the sun ages, its pressure increases, raising its pitch. By matching today's solar song with models, scientists determined the sun's current age, 4.6 billion years. This makes the sun millions of years older than previously thought. On our sundial, with 6 a.m. as its birth and 6 p.m. as its death, we are now at 10:36 in the morning. Humanity has existed for less than a second on this scale, enjoying the sun's warmth. But this will not last. The sun's heat will gradually increase until it becomes perilous for human life. Even today, during the sun's golden age, it poses dangers we are only beginning to comprehend. Using advanced imaging, scientists study sunspots, solar flares, and the hurricanes of particles they eject into space. The sun isn't alive, but sometimes it looks furious. On March 10, 1989, the sun ejected a massive cloud of charged particles. 3 days later, the resulting solar storm struck Earth. In Quebec, Canada, 6 million people were about to learn the sun's wrath. While the sun sustains life, it can also devastate our modern technological world. Our cities rely on complex power grids, and our communications depend on sophisticated satellites. All can be disabled by the sun. Billions of tons of high-energy particles erupting from the sun send powerful storms racing through the solar system. The growing understanding of these storms' destructive potential makes the work of space weather forecasters critical. At NOAA's Space Environment Center, they monitor the sun's violent moods. The 1989 storm was a dramatic eye-opener. A telescope in New Mexico captured a solar flare explosion, sending a charged hurricane toward Earth at over 1 million miles per hour. 3 days later, a massive electromagnetic storm engulfed the northern hemisphere. At 2:44 a.m., Quebec's power grid was overwhelmed by more than 1 million amps of current. Power stations failed in seconds, leaving 6 million people without electricity for 9 hours. The night sky glowed an unusual pink from the storm. The event caused hundreds of millions of dollars in damage. Today, teams monitor the sun 24/7, watching for sudden changes that could cause similar disruptions. They observe sunspots, dark, gnarly regions about the size of 14 Earths, and prominences, structures sticking out from the sun's surface. Both can generate solar storms. Scientists believe the sun's moods are driven by its complex magnetic fields. New magnetic fields constantly form as electrically charged plasma flows at different speeds around the sun. The sun's rotation tangles these magnetic lines, forcing some to emerge as dark sunspots and prominences. Plasma flows and field lines build up beneath sunspots. Eventually, the twisted field lines snap like rubber bands, causing explosions. When forecasters see prominences and sunspots, they alert for surface explosions. Sunspots can trigger solar flares, explosions with the power of millions of megaton nuclear bombs, sending radioactive particles into space. Prominences can grow and explode as well. Both can be followed by even larger eruptions called coronal mass ejections, where billions of tons of charged gas are discharged. These phenomena unleash high-energy particles carrying electromagnetic fields to Earth, disrupting conductive equipment like power lines. Researchers create their own prominences in labs to study these explosions. By feeding hydrogen plasma into a vacuum chamber and applying electrical currents, they simulate the process. Laboratory prominences are human-sized, while real ones on the Sun can be 60,000 miles long. In the lab, the entire event takes microseconds, but high-speed cameras allow scientists to watch in slow motion. Magnetic forces cause fields to arch and twist, with attractive forces merging prominences and repulsive forces making them explode. Normally, the solar wind carries about 1 million tons of charged gas away from the Sun every second. But during these explosions, additional particle clouds are far more dangerous. Earth's protective magnetosphere, which usually deflects particles to the poles, can be overwhelmed. At the poles, these particles interact with atmospheric gases to create the aurora. However, when strange lights appear far from the poles, as in Quebec, it signals intense solar storms breaching our magnetic shield. On September 6, 2005, forecasters monitored a strong solar flare. High-frequency radio communications were blacked out for aircraft and satellite phones over the Atlantic and Pacific. Airlines flying near the poles, which rely on high-frequency radio, were particularly at risk. During solar storms, this communication can be wiped out, blinding pilots and endangering passengers. Warnings allow airlines to reroute or ground planes. Other communication systems are also vulnerable. Satellites can be damaged, disrupting TV and cell phone signals. Beyond electrical damage and radio blackouts, these storms increase radiation risks. Solar radiation is dangerous for airplane passengers, but poses even greater threats for astronauts in space. In late October 2003, 3 huge sunspots appeared, one the size of Jupiter. A giant solar flare erupted, aimed directly at Earth. Astronauts aboard the International Space Station were in the path of this deadly radiation. We all experience one form of solar radiation, ultraviolet light in sunshine, which can cause sunburn and skin cancer. The ozone layer blocks the most harmful UV rays, and sunscreen offers additional protection. However, in space, protection is far more difficult. Space travel has always been hazardous, but early astronauts were unaware of solar storms and their radiation. On August 7, 1972, a massive solar flare occurred, one of the largest radiation storms ever recorded. It happened between the Apollo 16 and Apollo 17 missions. Had it occurred during a flight, the radiation could have been fatal. Scientists now know intense solar storms can be as dangerous to astronauts as gamma radiation from nuclear blasts. Solar flares release cascades of high-energy protons, which can pass through the human body, damaging chromosomes and potentially causing cancer. Large doses are lethal. Today, NASA uses space weather forecasts to protect astronauts. Astronauts training for space missions often learn about space weather's dangers unexpectedly. In late October 2003, aboard the International Space Station, an astronaut experienced the dangers firsthand during the Halloween storms. On October 28th, the second largest flare on record exploded from the sun's center, aimed directly at Earth. The Space Environment Center warned NASA, which immediately instructed the astronaut to move to the most shielded part of the station. For 2 days, he received radiation equivalent to a week's normal exposure or dozens of X-rays. Had he been outside during the storm, he would have suffered acute radiation sickness within minutes. There is one solar phenomenon with no known protection and an unknown cause: the superflare. Superflares are up to 10 million times more energetic than the strongest solar flares, lasting up to a week and making stars shine 1,000 times brighter. Astrophysicists have observed stars similar to our Sun that have produced superflares. One star, just 7% larger than our Sun, brightened by 10% for 4 days, releasing 1,000,000 times more power than the largest flare ever seen on our Sun. If our Sun produced a superflare, everything in space would be fried. On Earth, every power grid would fail. The extra heat would be like turning a winter day into a summer day, and auroras would be visible worldwide. While this might look beautiful, the radiation would likely be lethal, destroying the ozone layer that protects us from ultraviolet radiation. Humans might survive with extreme protection, but crops and marine plankton could not, collapsing the food chain and causing widespread extinction. Fortunately, stars with superflares tend to have them about once a century, and there is no evidence our Sun has ever experienced one. A theory suggests superflares might occur if a star has a giant Jupiter-sized planet orbiting very close, their magnetic fields intertwining and snapping like stretched rubber bands, releasing immense energy. If this theory is correct, we may avoid superflares, but we cannot escape the Sun's destructive aging. We are currently at 10:36 on the sundial. By 11:30, it will be too hot for humans. The Sun has grown 30% brighter since its birth 4.5 billion years ago, and scientists predict it will get hotter still, evaporating our oceans, melting Earth's surface, and ending life as we know it. We understand the Sun's birth, how it nurtures us, and the dangers it poses. But this is nothing compared to what happens as the Sun heats up and dies, unleashing an inferno that threatens humanity's survival. Death Valley in California, one of the hottest places on Earth, offers a glimpse of our future. As the Sun ages, it grows brighter, increasing in brightness by about 10% every billion years. Step into the distant future. The Sun's hydrogen fuel is slowly depleting, but nuclear reactions in its core are not slowing. They are accelerating. As fuel burns, core pressure drops, allowing gravity to compress the core further, heating the hydrogen and making it burn faster. This increases pressure from the core, restoring balance temporarily, but the cycle continues, making the Sun hotter and hotter. Eventually, the Sun will become so hot it will melt Earth's surface. On our sundial, we are at 10:36 a.m. Earth is currently in the ideal zone, not too hot or cold. As the Sun heats up, this habitable zone will move outward, scorching Earth and starting a catastrophic chain of events. We will lose jungles, forests, and farmland as deserts expand, turning the planet into vast sand dunes. Animals will be the first casualties of the increasing heat. Then, conditions will deteriorate further. Rising temperatures will speed up the removal of carbon dioxide from the atmosphere, which plants need to survive. Plants will virtually disappear, and with them, the animals that depend on them. The life-giving heat will become so intense it kills Earth's rich biodiversity. As plants vanish, oxygen levels will drop, making it harder for humans to breathe. We will also lose most of our food supply. Yet, even at this stage, some humans may persist due to our adaptability. Scientists disagree on the exact timeline, but in about 1 billion years, at 11:30 on our sundial, average temperatures could reach 160 degrees Fahrenheit. Daytime heat could be lethal. Survivors might live underground, emerging only at night. Humanity would have two options: build increasingly sophisticated artificial environments on Earth or relocate elsewhere. To survive as a species, we will likely need to find a new home, especially once Earth's water begins to vanish. As the sun grows hotter, more water will evaporate until our oceans disappear. This will make human life on Earth impossible. In Death Valley, the Badwater Lake dried up 10,000 years ago, leaving salt flats. This landscape is an eerie preview of Earth's future, appearing utterly alien. From space, Earth will no longer be a blue and white planet of water and vegetation. It will resemble Mars. By then, humanity must have left, becoming mere spectators to the sun's final acts. The sun will swell and change color from yellow to red, becoming a red giant, an old star entering its last phase. It will fill the daytime sky. The atmosphere will be gone, making it seem like looking into space. This will occur roughly 6 to 12 billion years from now, nearing dusk on our sundial. Though an old star, the sun will be more active than ever. Having exhausted hydrogen in its core, it will burn helium at even higher temperatures. Energy radiating from the superheated core will push the sun's outer layers outward, causing it to expand. As it grows, its surface will cool, giving it a redder hue. While the outer layers cool, the sun's increased size brings it closer to us in the solar system, much like stepping nearer to a fire. Earth will feel intensifying heat. The red giant phase is extremely dangerous for a planet like Earth. The sun will become vastly brighter and larger, its heat frying our planet. Earth's surface will have long since melted. Worse is yet to come. As the sun grows unstable, violent thermal pulses will cause it to go into overdrive, expanding 1,000-fold in diameter. During some pulses, it may expand to the size of Earth's orbit, swallowing the inner planets. Anything in its path will be vaporized. Mercury will burn up like a giant meteor, followed by Venus. Will Earth suffer the same fate? As heat waves tear through the sun, it will shed billions of tons of material into space, weakening its gravitational pull. This might allow Earth to drift away and escape incineration, but scientists are uncertain. Even if Earth escapes, it will be an unrecognizable molten world. It is approaching 6 p.m., dusk on our sundial. The sun's life as a burning star is ending. However, it is not massive enough to explode as a supernova. Only stars over 8 times the sun's mass do that. Instead, it will shrink into a white dwarf, glowing faintly for hundreds of billions of years. So the sun ends not with a bang, but a whimper. The magnificent star that provided Earth with heat and energy for billions of years will become a small, faint object not much larger than Earth itself. The sun gave us life. With its death, all life on Earth will perish. If humanity still exists, we will be among the stars. So, the next time you enjoy the sunshine on a beach, remember it will not last forever. If you found this journey through the life of our sun fascinating, Please show your support by subscribing to the channel, liking this video, and sharing it with others who might be curious about the universe. Your engagement helps us continue exploring these incredible stories. Thank you for watching.